Hello, welcome to Future-Proof Your Data Center with NVMe Technology. This is an SDC2020 presentation. I am John Kim, Storage Marketing Director for NVIDIA, and I am presenting on behalf of NVM Express. In today's presentation, I'm going to cover future-proofing your data center, then what's new in the NVMe 1.4 specification, what's new in the NVMe over Fabrics 1.1 specification, new management frameworks you can use to manage NVMe storage, and then what is new, different, or faster in NVMe over Fabrics transports and networks. When it comes to future-proofing your data center, of course, it's not possible to buy any piece of equipment or technology that will last forever. But what you do want to do is make design decisions and purchasing decisions that will maximize your ability to support new technologies, faster products, faster networks, and more flexible decision-making for the next several years. So of course, in future-proofing, you want to pick the best servers, operating systems, hypervisors, and containers, probably with a focus on supporting microservices and containerization going forward. You also want to have a scalable, fast network that allows you to upgrade the network speeds. You want a security strategy that's able to respond to different types of architectures and different types of threats, and it's easy to upgrade. It's likely that you want to move towards a DevOps approach with the ability to do scalable monitoring and automation or telemetry across your data center. But the focus of today is storage. So on the storage side, it's important that you not only be able to handle faster storage, more reliable storage, but build an infrastructure or use storage technologies that can take advantage of faster storage products, faster storage networks, and new features coming in storage, such as what's new in NVMe. Here are some storage trends to account for when planning the future of your data center. So first, as most people know, almost all primary and secondary workloads have moved or are moving to flash storage and away from hard drives. Hard drives do remain popular for archive, for backup, and for cloud storage, especially for large objects including photos and videos. NVMe is dominating and replacing other types of flash storage in terms of form factor and interface. This is shown by the fact that NVMe storage revenues, including both local NVMe and NVMe over Fabrics, are expected to grow at almost 30% per year each year for the next 5 years. For storage architecture, there are actually two different movements that almost sound contradictory. In large enterprises or in the cloud, there's a push to disaggregated storage, where storage moves out of the local servers and into centralized network storage that can be allocated, shared, and reallocated as needed. In enterprise deployments and in smaller data centers, there is also a push to implement hyperconverged infrastructure. This tends to have many servers, each of which have some local storage, but the storage is then shared or reallocated or virtualized across the servers as needed. In both cases, more storage networking is used to connect the data, whether it's for the centralized disaggregated storage or for the shared hyperconverged storage. There are new types of flash storage coming. So persistent memory is creating faster storage, which can be deployed as either SSDs or as a type of higher capacity, less expensive persistent memory. And then computational storage is on the horizon with the ability to have storage that performs searches or indexing or compressions or other operations on the data. These storage trends help explain the growing popularity of NVMe over Fabrics, which allows sharing of NVMe storage with a very efficient block protocol over a network fabric. NVMe local storage in a server is of course very fast and efficient, but usually limited to local use, and it's difficult to share or to access across the network. So there is always a desire in data centers to share storage and network it to improve provisioning, for cloud, virtualization, or container storage, to simplify data and workload migration, and to improve efficiency and data protection of that storage. There's a desire to have the performance and the semantics of the NVMe protocol, which is more efficient as a block protocol and supports features like multi-queue that are well supported for flash, but to run that over a network. And thus there's the ability to run NVMe over Fabrics, giving you all the benefits of the NVMe protocol, as well as the ability to share the storage and connect to it over a network. So let's talk about what's new in NVMe version 1.4 and then what's new in NVMe over Fabrics 1.1. Some of the major new features in the NVMe 1.4 specification include persistent memory regions, I/O determinism, NVM Sets, Asymmetric Namespace Access, and enhancements to some existing features such as controller memory buffer, host memory buffer, the Sanitize command, and some other commands. There are some additional new features that we will not cover in detail today, but they generally make it easier or better or possible to make data more persistent, to prevent it from being erased, to recover data from a failed device more quickly, or to improve endurance by managing wear leveling. Let's talk first about I/O determinism. The first major feature here is NVM Sets. These create quality of service or QoS isolated regions on an SSD. In this case, in this example, named NVM Set A, NVM Set B, and NVM Set C. Each set can contain multiple namespaces, and the important characteristic is that I/O to one set does not affect the latency or response time or the quality of service for a different set. So in this case, I could have a lot of traffic going to NVM Set A, and that should have no effect on the performance of any traffic going to NVM Set B or NVM Set C. This is important for making application performance more predictable and more consistent in the data center. If your NVMe device supports it, you can have NVM sets that have predictable latency. This means that the set will provide a predictable, consistent latency within a fairly tight QoS window as long as you're reading from that set during one of its deterministic windows. Each set will spend the most of its time in a deterministic window, where again the response time is very predictable and consistent, but it does go through periodic shorter periods of non-deterministic behavior where it's doing wear leveling or garbage collection or other maintenance. So you can have, by overlapping different sets which have offset windows, in other words, their deterministic and non-deterministic windows happen at different times, you should be able to get consistent performance where it's almost always predictable and consistent in terms of latency and response time. Another change in NVMe 1.4 is an enhancement to the existing controller memory buffer, or CMB feature that was first supplied in NVMe specification 1.1. The controller memory buffer is a region of memory on either an NVMe device or on a special network card or controller card that allows for direct memory writes from the host. Previously, there was the possibility of a mismatch or misunderstanding between the host and the NVMe controller about whether or not to use a controller memory buffer. So this update ensures that that direct memory access will only be performed if the host and the NVMe controller are in agreement about using CMB. While the controller memory buffer can be used for both local and networked NVMe storage, it probably has a much greater benefit for NVMe over Fabrics, connecting over a network. The reason is that the controller memory buffer, which can live on the network card or on the SSDs, allows the network card to store the command queues and even the actual data there on the CMB instead of storing it in host memory. This avoids interrupting the CPU on the storage target and reduces the amount of latency. It also allows you to take full advantage of a faster PCIe Gen 4 interface if the network card and the SSD support PCIe Gen 4, even if the CPU might not support PCIe Gen 4 and is still running PCIe Gen 3. So utilizing a CMB feature can reduce latency, increase performance, and free up memory that on the host that can be used to run the applications instead of for storing the data transfers between the NIC and the SSDs. This slide illustrates how a CMB could be utilized to improve performance for NVMe over Fabrics. On the left side, we see traditional direct memory access, or DMA, where data going through the NIC or network card is first passed through the CPU and put into the target system DRAM before it's transferred to the NVMe SSD. On the right side, however, by using a CMB region on the SSD, the NIC is able to transfer data directly to the CMB or controller memory buffer region on the SSD without going through the CPU and without first placing the data in the system DRAM. The CMB could also have a PMR, or persistent memory region, which allows you to guarantee that any data placed there, for example, in a cache or data that's placed there with or metadata, will be saved even in the case of a power outage. CMB can also be used for peer-to-peer data transfers or direct copies between SSDs, where data can be transferred from one SSD to another, again, without having to pass all the data through the CPU and the CPU memory controller and the main system memory. Many of the additional features in NVMe specification 1.4 deal with supporting persistence of data or with improving manageability or monitoring of the storage. On the persistence side, this generally means guaranteeing that data that you store in memory either will survive a power cycle, or memory that you store or data that you store on the SSD will not be erased, either for some period of time or forever. So for example, namespace protect allows you to prevent a namespace from being erased or deleted either until the next power cycle of the SSD or forever, depending on which setting you choose. So this is really good if you want to store, for example, logs or important records of financial transactions or medical records, and you want to make sure that they cannot be deleted for compliance purposes. You could then specify that the information is protected until the next power cycle, or again, protected forever, so it cannot be deleted. The persistent memory region is usually a section of RAM or DRAM or SRAM on the SSD, which has a guarantee that data written there will survive even if power is lost or power is cycled to the SSD. Typically, this is, again, DRAM or SRAM, which is backed up by either supercapacitors or batteries, and if the power is lost, the data is then flushed to the NAND or non-volatile part of the SSD, guaranteeing that the data is saved. This would make it really useful for a write cache, for file system metadata, or for other housekeeping data or logs that need to survive to record, for example, to roll back transactions or ensure a good record of all activity on that SSD. And likewise, the persistent event log also is ideally suited for that because it records or logs specific events related to the SSD and keeps them so that you can go back and check on them for failure analysis or performance analysis or other management tasks. On the management side, there are several new features that assist in rebuilding or recovering data in case you have a failed device or a failed section of a device. So for example, the Rebuild Assist feature identifies which logical block addresses, or LBAs, can or cannot be recovered. So then the storage software or the storage controller can decide to recover that data, whether it wants to keep trying to recover that data from this particular SSD or wants to recover it from a different location or a different SSD, perhaps a backup or a mirrored copy. The read recovery levels allow the storage controller to manage, to balance the amount of read latency versus the error recovery efforts. So you may have a case where you can read the data, but it's going to take extra time to rebuild it or recover it. Then you may decide to read the data more quickly from a different location if read recovery levels lets you know that you can recover this data, but it's going to take a very long time. Endurance groups and some hints related to that allow the storage controller or the storage software to help manage wear across NVM sets. So this assists with wear leveling because you can then, instead of the wear leveling and the endurance management being something that's only within the SSD and a sort of black box feature, so to speak, now you have a case where the storage software or the storage controller can use hints or directions and help tell the storage devices or the SSDs how endurance should be managed or give preference on how the wear should be allocated. And that's in the performance and endurance hints as well. The verify command allows the software or storage controller to check the integrity of the data on an NVMe device without copying it completely to the host. So if the verify command goes in and says, I'm going to make sure I can read this data and the metadata associated with it, and it will report either success or an error message, but it does not actually copy all the data to the controller. Because the controller in that case doesn't actually need all the data, it just needs to verify that the data was stored safely and is still readable. So these commands generally increase the reliability, the scalability, and the manageability, as well as perhaps the efficiency or longevity of the NVMe storage. Now let's talk about what's new in NVMe over Fabrics 1.1. The major changes are the ability to use TCP/IP as a transport, the addition of domains and divisions, persistent controller discovery, I/O queue deletion, which also is known as a graceful disconnect option, submission queue flow control, which is basically now optional, and then the ability to specify the RDMA queue pair controller ID when you set up an RDMA queue pair. So we'll focus on mostly the first three of these as we get into more detail. Sometimes the question arises, why do we need NVMe over Fabrics supported on TCP in the first place? So a brief history of NVMe over Fabrics is in order. It was supported first just on RDMA, and then shortly afterward it is supported on Fibre Channel. Both RDMA and Fibre Channel provide high performance, low latency networks, which are often dedicated just for storage in the case of RDMA, or always dedicated for storage in the case of Fibre Channel. However, some customers complain that they didn't have the right hardware, or they didn't want to set up RDMA networks or Fibre Channel SAN. RDMA networks actually today can run over standard network cards and switches, but for the best performance, they require special RNICs or RDMA-enabled network cards. And Fibre Channel SAN, of course, requires Fibre Channel HBAs and a Fibre Channel switch. So there are customers who said, I want NVMe over Fabrics, but I don't want to implement RDMA, or I don't want to implement Fibre Channel. Perhaps I have a lot of servers which already have Ethernet adapters. They're connected to an Ethernet switch, but those adapters and that switch really aren't ready to do RDMA. So TCP, of course, is everywhere. Every server has a TCP connection and the capability to do it. All networks support TCP, even if they also have Fibre Channel or InfiniBand or other RDMA solutions running. And it turns out that TCP, if properly configured, can provide pretty good performance for NVMe over Fabrics. So that's the first major change in NVMe-oF 1.1. And you can see more if you go to the SNIA NSF webcast from January 2019. The link is here on this slide. So again, fast performance, and it can be accelerated if you have special network cards, or you can get performance which is okay, not as good as RDMA or Fibre Channel, but pretty good using standard network cards and standard switches. Another major section of improvements to NVMe over Fabrics is in the ability to support multipathing. This is a combination of changes to the NVMe 1.4 specification and the NVMe over Fabrics 1.1 specification. So first, it's important to understand that multipathing was added back in NVMe 1.1. However, at that time, it assumed that all controllers were identical and had equal performance and equal preference or equal priority. So if you had a host, it was connecting through, say, to a namespace through two different controllers, you had to assume from the host and the software level that each controller offered exactly the same performance, and whichever one was available or chosen randomly would be used. However, that's not always the real case, or the preferred case. So in NVMe 1.4, they added Asymmetric Namespace Access. This means that the controllers can be different, the controllers offering different paths to a particular namespace, and the access paths can be given preference, whether it's a local access with NVMe or over a network with NVMe-oF. So now you could, for example, have a more powerful controller that is your preferred controller, which gives better performance, and there could be an older or smaller or less powerful controller, which is the backup controller and is only used in case of failover of the primary path. So now you're able to specify that controller A, for example, is my preferred controller and controller B is there and it's connected, but it's only used if controller A fails or is too busy. Another change was in domains and divisions. This now means that an NVMe subsystem can be subdivided into domains, and each domain can be powered on or power cycled or managed or faulted separately. So this is really good for large NVMe subsystems and for non-disruptive operation, because it means that you can cycle or change or troubleshoot one domain without having to stop and restart the entire system. In this slide, we're illustrating how you might use asymmetric namespace access, and then on the right side, we're illustrating the use of domains. So first, let's look at ANA, or asymmetric namespace access. So in this case, we're showing that there's controller A and controller B, and actually in contrast to what I said on the last slide, controller B is the bigger, more powerful controller, and the green line shows that the preferred path to namespace 1 goes through controller B. So the host going to namespace 1 will go through controller B, and then the host going to namespace 2 might prefer the blue path, which is going through controller A. So in case either controller fails, access to both namespaces can continue through the other controller. So if controller A fails, you'll still be able to get to both paths through controller B and vice versa. But you can express a clear preference for different namespaces and different hosts. In terms of domains, on the right side, we see that we have different domains, and in case one fails, so let's say domain 3 fails, instead of having to reset all the storage in the entire subsystem, I can reset just domain number 3, perhaps do some troubleshooting or a reset or a power cycle, and then get back to work on domain 3. And meanwhile, any workloads or I/O going to domain 1 and domain 2 is not interrupted. So that's an advantage of domains when you have a larger system, which may have multiple namespaces or a lot of storage that you want to separate into different domains. Another category of improvements in NVMe over Fabrics 1.1 is in the discovery and transport area. So first we have persistent controller discovery. So of course discovery already existed, but in NVMe over Fabrics 1.0, the original specification, discovery is and was a one-time deal. So if you discovered a storage controller and then something changed or you lost track of it, you would have to go do a new discovery because otherwise you wouldn't know about any changes. Now, with persistent controller discovery, if there are new connections or different changes, this discovery is persistent and the host can be notified of the changes there at the controller level. For example, there could be new storage or new capacity added or new features supported, and now you can find out this information through a persistent discovery instead of doing a new discovery. A second new feature in the transport area is an I/O queue deletion. It's also known as the graceful disconnect option. So normally, in NVMe over Fabrics 1.0, you have a host to controller association, and if anything goes wrong with any of the I/O queues, you had to kill the whole association, kill the connection, and reestablish that connection. So that was fine if you had one queue, but it got very messy or inconvenient if you had many queues. Now, if one queue with NVMe over Fabrics 1.1, if one queue causes problems or hangs or gets stuck, you can delete just that queue without terminating the host controller association. And all the other queues can continue their I/O, continue running their applications without interruption. So this is something which is specifically just for NVMe over Fabrics, and it's good for large storage systems which are more likely to have many queues going and many workloads running on different queues going to the same storage system. Some other changes which are more minor, and we'll just mention briefly here, are that if submission queue flow control is now optional. This is because it turns out a lot of people were not using it, and they weren't using it because it could be done at a lower protocol level or at a lower transport level instead of in the NVMe over Fabrics protocol. So it's still there, but it's now optional since not everyone was using it. Another difference is that the RDMA queue pair can now specify a controller ID during creation. Previously, when you set up an RDMA queue pair, I think you then had to go back afterward and tell it which controller ID you wanted to use. But now when you create the queue pair, you can go ahead and specify the controller at that time. Management frameworks. So large-scale storage is not practical unless you have good management. So let's dive more into that aspect of storage networking. So there is an evolving new set of management standards for NVMe and NVMe over Fabrics storage, which is a combination of DMTF Redfish plus a set of APIs from SNIA called Swordfish. So the reason you need this is it turns out that the NVMe management commands by themselves are not very well suited to large-scale storage implementations, especially if you have multiple controllers, many devices or many SSDs, and many hosts that have to discover, access, and use these different storage devices and different storage controllers. So what Swordfish does is it defines a logical fabric management model that can be used for both NVMe and NVMe over fabrics. It's a model that supports the different fabric types, so it works with RDMA, it works with Fibre Channel, and it works for TCP/IP. That one model can be used to manage all the fabric-connected systems and services. So this is not a case of either or. It's not Swordfish versus Redfish, but Swordfish is actually an extension of the Redfish API. So the Redfish API is a RESTful interface over HTTPS in a JSON format, and it allows, it's a set of APIs that allow you to manage storage, and then Swordfish is a management framework that takes advantage of the Redfish API to let you do discovery and management and allocation of the storage systems and the volumes within. So Swordfish is actually very recently made available. It was just released in June of 2020. This overview includes use case mockups, NVMe-specific property schemas, models for both NVMe and NVMe over fabrics. You can find resources about this on the SNIA website if you go to snia.org/forums/SMI, which is storage management, and then /Swordfish. You can also find the mockups at swordfishmockups.com. So the next steps for Swordfish are to develop a detailed model, an overview, and a mapping document that will map between Redfish, Swordfish, and the NVMe and NVMe over fabric specifications. So right now we have the model framework, but we don't necessarily have a mapping of all the specific commands to the different features and commands in NVMe and NVMe-oF. So what else will be coming is that Swordfish will add usage guidelines, and this is being developed in the SNIA Scalable Storage Management Technical Working Group, along with the NVMe and DMTF organizations. So it's expected that Redfish and Swordfish will have profiles and will also have a conformance test program that will allow vendors and customers to verify that a particular storage controller or storage software is compliant to the Redfish Swordfish management model. So I have new and improved, faster NVMe devices. I have a better management model. Now I need a faster, better, modern network to transport that data between the hosts and the controllers, or the controllers and the devices. So let's see what's new on the transport side of NVMe and NVMe over fabrics. The first change is on the PCIe bus. So PCIe Gen 4 as a specification has been around for several years, but it was not widely supported until recently. Now there are SSDs coming out that support PCIe Gen 4. This is important because it doubles the speed. It's twice as fast as PCIe Gen 3, supporting up to 16 gigatransfers per second per lane with 128 over 130-bit encoding. This means that you have up to 63 gigabits per second if you have 4 PCIe lanes, which works out to about 7.8 or 7.9 gigabytes per second for a typical 4 lanes used for the 4 lanes typically used for one SSD. So again, there are SSDs available now. I've got pictures of 2 of them here, which support PCIe Gen 4. There are also CPUs that support it. So while Intel doesn't have the support yet, but should have support fairly soon, AMD, ARM, and Power CPUs all support it. And there are also GPUs and network cards that support PCIe Gen 4. So it's possible now to have a PCIe Gen 4 network card that transfers NVMe over Fabrics data directly to a PCIe Gen 4 NVMe SSD, again possibly using the controller memory buffer feature that we talked about earlier. So this speed is now available but again PCIe works locally. Another area of transport that has been upgraded is InfiniBand. So InfiniBand is very popular with high-performance computing, or HPC customers, and also for artificial intelligence and machine learning. So for example, if you look at the DGX supercomputer from NVIDIA, it has built-in InfiniBand connections for connecting the different DGX computers to each other, as well as for connecting to storage. So the latest updates in InfiniBand are going to what HDR, which means 200 gigabit per second connections, and there have been enhancements to in-network computing. In-network computing is the ability for the network itself, the combination of the adapter and the switch, to perform data reduction or collective operations on the data while it's moving across the network. So this is a specialized capability that is mostly designed for HPC, artificial intelligence, and big data, but it can greatly speed up any distributed data processing that has to do these kinds of operations. So InfiniBand can also offload the data transport to the adapters, and the adapters can accelerate NVMe over fabrics, as well as some other things like storage encryption. And the network supports adaptive routing and self-healing capabilities. So it's a very fast network. It's out there at 200 gigabits a second today, but it's generally used just in HPC, AI, and some cloud implementations that are supporting big data or AI. On the Ethernet side, there are actually a lot of changes and innovation happening. So first of all, there are 400 gigabit switches available. Now, these switches can support 400 gigabit per second links between each other, but the maximum speed to one host right now is 200 gigabits per second, which is typically a limitation of the PCIe interface, because even with PCIe Gen 4, you can only get a little bit over 200 gigabits per second through one network card. But the 400 gigabit per second links between switches let you improve the design of the network or the topology, because you can have a much more efficient network when you build a very large network, because you have fewer connections between switches. Another change comes on the RDMA side. So there's something now called zero-touch RoCE. This means that you can run RoCE without network changes. Traditionally, RoCE, which is RDMA over converged Ethernet, was very fast, almost as fast as InfiniBand, but you had to have special adapters and you had to modify the switch settings in order to get it to work. There were a bunch of customers who, it turns out, on the enterprise side, did not want to. They said, I want the performance of RoCE, but I don't want to modify my switches. I don't want to, or I won't, or I can't. Now with zero-touch RoCE, there's the ability to get the performance advantages of RoCE, and it runs, and if you make zero changes to the network, it runs almost as fast as if you did the network switch optimizations that were traditionally required. So zero-touch RoCE, a little slower, but still much faster than TCP, and gives a very efficient RDMA connection across Ethernet, but now without having to modify the switch settings. Another change on the Ethernet side is something called the Data Processing Unit, or DPU. So there are multiple vendors who are out there now, a combination of large vendors and startups, saying that they have a DPU, and the key is, well, what is a DPU? A DPU is usually a SmartNIC, which also has programmable CPU cores on board, so it can run and accelerate the data plane, which can include TCP traffic or RoCE traffic. It might include NVMe over fabrics, but they can also run the control plane on that network card or on the DPU. So this is like a very special SmartNIC, which can run software-defined networking, software-defined security, a next-generation firewall, or even an NVMe over fabrics controller on the cores on that card, in addition to having all the standard SmartNIC offloads and accelerations, which are for like TCP or RoCE or NVMe over fabrics or encryption or things like that. So a DPU is a fairly newer concept, but it gives you greatly accelerated networking and security and storage acceleration, as well as the ability to do additional management and virtualization on each host. So it's a very interesting concept, and these are generally supporting only Ethernet. And then there are also NVMe over TCP offload cards or other accelerators which are coming out, which let you accelerate NVMe over fabrics over TCP. So traditionally, NVMe over fabrics over TCP, which is fairly new from 2019, from the end of 2019, is very convenient, but it's not as fast as RDMA or Fibre Channel. So if you add accelerator cards of some sort, which interestingly are not the traditional TCP offload engines, they're not tow cards, then you can get faster NVMe over TCP performance, but again, you might not have to change your switches or switch settings. But in this case, you do need a special adapter card, and you can't use just your regular plain old NIC that was in the servers. So that's some very interesting changes on the Ethernet or RoCE or TCP transport side for NVMe over fabrics. And of course, not to be left out, Fibre Channel has also seen some new upgrades in terms of speeds and capabilities. So first of all, Fibre Channel keeps getting faster. So the Generation 6 Fibre Channel, which is called 32G, it actually runs at about 28 gigabits per second, but that's been seeing wider deployments. That's been available for a few years, and there are actually now more servers that come with 32G Fibre Channel and more switches that support it. But just announced in the last 2 weeks is the shipment of Generation 7 Fibre Channel, also known as 64G Fibre Channel. So it runs at about 56 gigabits per second. So it doubles the speed. It also reduces the latency compared to Generation 6 Fibre Channel. And it's actually shipping now in Q3 of 2020. So there's faster Fibre Channel available, and both Gen 6 and Gen 7 support NVMe over fabrics, or FC NVMe. And then there's also FC NVMe 2, which adds some improvements. And the main improvement I'll mention here, I think there's several, but is sequence level error recovery. So this is something where you normally have in Fibre Channel with NVMe over fabrics, you have an exchange. But if you had one sequence that was bad or one little error in the exchange, you had to throw out the whole exchange and terminate the association. This is no longer required because SLER, sequence level error recovery, can throw out and replace just the faulty exchange and then maintain the association and maintain the traffic flow so you don't have to kill and reestablish the association between that host and controller. So this is great for resilience and performance and scalability for customers who want to run NVMe over fabrics on Fibre Channel. And seen here, I've got a picture of a Broadcom Generation 7 Fibre Channel Emulex adapter and a Brocade switch. So in summary, to future-proof your data center with NVMe technology, you need to plan for technology changes. As we mentioned at the beginning, it's not possible to buy any one storage device or network card or switch or software that will necessarily last forever and be immune to all changes. But you can plan to get the right software and right networking equipment and right technology standards that will last for several years and be ready to accept and ready to support faster storage devices, faster servers, faster networking, PCIe Gen 4, and so forth. So some of the things that you can do to future-proof, or meaning next several years, your data center, are to move all your primary storage to NVMe and NVMe over fabrics whenever possible. So that's going to give you access to the newer form factors, new SSDs, to persistent memory, and give you better performance across your applications. A second change is have your network ready to support faster speeds. So if you're on InfiniBand, you want to make sure you're getting ready to support the HDR or 200 gig InfiniBand. If you're on Ethernet, you want to have adapters and switches that can handle the 25 and 50 gig connections, or maybe even 100 gig connections to the servers, 100 gig connections to the, or 200 gig connections to the storage, and then 400 gig connections from switch to switch. If you're on Fibre Channel, you want to be making sure that your adapters and your switches are supporting Gen 6 or Gen 7 Fibre Channel, the 32G and 64G Fibre Channel, so that you can handle, because not only gives you more performance, but Gen 7 Fibre Channel, 64G, reduces latency, and both Gen 6 and Gen 7 can support FC NVMe, meaning NVMe over fabrics on Fibre Channel. And if you're running Ethernet, you actually want to make sure you're ready for RDMA support, because there are an increasing number of applications besides NVMe over fabrics which can benefit from RDMA, and these are generally in the artificial intelligence and the big data area. So applications like Spark or anything related to CUDA or many of the machine learning algorithms are designed actually to support RDMA and gain benefit from it. So I believe there will be a big explosion in the use of commercial AI in enterprise and the cloud. And to take full advantage of that, your network or the Ethernet part of your network should support RDMA. In terms of your vendors and staff, so some of you are developers, some of you are vendors, some of you are end users, but you should be asking your vendors and your IT staff, do your NVMe SSDs support NVMe 1.4? Do they support PCIe Gen 4? It doesn't make sense at this point to be buying PCIe Gen 3 SSDs or PCIe Gen 3 network cards or motherboards if you can get PCIe Gen 4 support. Do your storage systems support NVMe over Fabrics? And ideally, are they going to support NVMe over Fabrics 1.1? I suspect most of the systems that support NVMe-oF today support 1.0, but can be upgraded to support NVMe over Fabrics 1.1 with a software upgrade on the storage system. But you want to ask about that and verify. Again, you want to ask your network vendors and network partners, do you support RDMA? Or do you support an NVMe over TCP offload or acceleration? So if you're not going to do RDMA, but you're doing Ethernet, then you want to be able to get high performance from NVMe over TCP. And to the storage vendors and storage device makers, you want to ask when and how will they support Redfish and Swordfish for management, because these are the evolving standards coming from DMTF and SNIA, and they're going to simplify management of storage devices, and I think that they will be adopted pretty quickly. So you want to make sure that your vendor is on board with the Redfish and Swordfish initiatives. So I'd like to thank you very much for watching this session here at SDC, and we would like to ask you to take a moment and give us a rating. So tell us what you thought, give us a rating. Your feedback does matter very much to me as the presenter and to all of us at SNIA who put on SDC, and we would love to hear what you think. With that, thank you very much for watching, and we'll be happy to answer any of your questions in the Slack channel.